Okay, I tried recording earlier and the microphone wasn't on, so there goes a waste of a few minutes, but that's okay. So we're going virtual tonight, and I wanted to go over some material. I'm going to post three 15-minute videos, about 45 minutes worth of me talking, and then the balance of time for you to work problems, which I shall upload to the web page. Um, see, I started going already here with this, but we can go back and review it. I was going to talk today about a couple of things. One of them is so-called literal equations, as opposed to just equations and variables. And I had shown this little equation. I said, hey, we were solving these very simple equations for one variable x last time. And if I have something like 5 plus 3x is equal to 20, we can certainly solve that for x, subtracting 5 out from both sides. If you do something to one side, you have to do it to the other. And that's going to bring down your 3x, and 20 minus 5 is 15. Divide both sides by 3, and you'll get x is equal to 5. So that's solving an equation for a variable x. Now, when we start looking at little equations, we are you looking at formulas that contain a multitude of terms, and they all mean something. They're not just variables for the sake of variables. So, for example, the very simple one here would be Kelvin temperature units is equal to degrees C plus 273. And degree C is your centigrade or Celsius temperature, and 273 is the constant that relates these two things. So 0 degrees Celsius is 273 Kelvin. We don't say degree Kelvin, we just say Kelvin. And this is called the absolute temperature scale, because if you go to negative 273 degrees C, that's equal to 0 Kelvin. And there are no temperatures below 0 Kelvin. This is the coldest temperature, so you can't have negative temperatures. 0 Kelvin is absolute zero. And we use these absolute scales, be they Kelvin or Rankine, which you may use in the gas industry, and we'll certainly address that. What we say is that we use these in gas laws because we don't have to worry about uh, zeros in the denominator or negative numbers and negative volumes. So we need an absolute temperature scale. As a matter of fact, another example of a literal equation would be something like PV is equal to N times R times T. Well, this is an example of the ideal gas law. And P stands for pressure, V stands for volume, N stands for something called number of moles, R is a proportionality constant, and T is a Kelvin temperature. And we could rearrange this for any variable that we want. And that's what you need to get used to doing. So, for example, if I say rearrange this for volume, well, volume is V, and that's going to be equal to, I'm going to divide both sides by P here, nRT over P. If I asked you to solve this for temperature, well, temperature, I have to divide both sides by nR, so that's going to be PV over nR. So you have to become very fluent rather, in manipulating equations. Let's take a look at some other examples. This is a good one here. It says, I have an old book of engineering problems, and it says, in the study of forces on the wing of an aircraft, the equation M is equal to R times L minus X is used. Now, these terms, I'm not sure what they stand for. The book doesn't tell me, but this is their equation, which relates these forces on the wing of an aircraft. Imagine L stands for length or something, and I'm just not really sure. But it doesn't matter because they're saying solve for L. So solving for L means we want to say L equals. L is the subject of that sentence. So first things first, we have this R, and it's multiplying this term L minus X. So we can do one of two things. We can go ahead and distribute if we wanted to, or we can manipulate this equation a little bit more. First of all, before we go here, let's say that I divide both sides by r. M over r is equal to L minus x. Okay, that's perfectly fine. So when I go ahead and do that now and rearrange things, I want to add x to both sides, get rid of it on that side, and add it to the other side. So I'm going to have something like this. M over r plus x is equal to L. Now that's fine, but it's not quite tidy enough. I'd like to tidy that up a little bit and make this sort of maybe one term over here. And if you want to find a common denominator, you can multiply by r over r. And multiplying by r over r is just the same as multiplying by 1. So when I do that, I'm going to get m plus xr over r is equal to L. And that's our answer. L equals m plus xr over r. Now again, it's not too important what these terms mean, just so that you can go ahead and figure them out. That x is a variable, not a time sign. So let's continue on looking at a couple of other examples. It says, in analyzing heat transfer through a wall, an engineer must solve the equation, well, Q usually stands for heat, is equal to Ka times B minus C over L. And again, these are probably some constant of proportionality, maybe some area. I don't know what these constants represent. It's not that important for our discussion of manipulating equations, but just get used to manipulating them. So the question is, they want you to solve for B. B equals. Well, why don't you just pause for a minute and see if you can go ahead and do that. And then we'll come back and check it out. Okay, so what I'm going to do is the first things first. I'm going to get rid of this L because we're trying to get B on one side. Look here, though. Maybe first we should try to get B minus C on one side. So B minus C is equal to, I'm going to multiply both sides by Q, or by L rather. So QL, and then I'm going to divide by Ka, both sides. Ka, and I'm almost there. I want to solve this for B. So if I add C to both sides, I get B is equal to QL over Ka plus C. And again, I would like to make this look a little tidier. So I'm going to multiply by Ka over Ka on this last term. So I have a common denominator. And I get B is equal to QL plus CKA all over Ka. And that would be the way I arrange that formula. So hopefully, you see, these aren't so bad. Let's take a look at something where we might have to do some more manipulation. We'll do a few more examples, and then I'll give you some problems to look at. I'll upload them. Let's take a look at one here. It says, if I've got two or more variables, and I want to solve, sometimes we use subscripts for two or more variables representing the same quantity. So for example, you might see x sub 1 and x sub 2. And they might both represent lengths, for example, but we have two different ones specified. You might see v sub I and v sub f. These might be initial velocity, for example, and final velocity. So these subscripts just enable us to differentiate between like quantities but with different values. So let's take a look at just some equation. And I don't know, we'll just come up with one here. AS1, that's some constant times S1. S1 might be a displacement, might be a length, plus CS2 is equal to 3A times S1 plus A. And again, this doesn't have to stand for anything in particular, just getting used to solving for variables. So what do we want to do here? We want to come up with a sentence that says S1 equals. In other words, how do we take this big messy equation here, which really isn't terrible, and go ahead and solve this for S1. Now, first thing I would do is I would go ahead and distribute so I can collect like terms. So let's get back to, we'll get back to that later. First things first, I'm going to go AS1 plus CS2 is equal to, now I have to multiply 3A times S1, 3A S1 plus 3A squared. Well, now I'm in a position to bring all of my S1s to one side and all of my other terms to the other. I could subtract 3A S1 from both sides, but then I have a negative quantity over here, and I'll have to play with that later. So let me go ahead and subtract AS1 from that side and AS1 from that side. When I do that, I'm going to have CS2 is equal to 2AS1 plus 3A squared. And I think we're in a position now where we're getting pretty close to our answer. So I'm going to get my A squared on that side. So I have CS2 minus 3A squared, and that's going to be equal to 2AS1. My final step then is just to go ahead to isolate S1, divide both sides by 2A, and I would get S1 is equal to C S2 minus 3A squared over 2A. So that's the way we're going to rearrange that particular equation. All right, we'll do a couple more examples, and then I'll upload this and get it on your class page, along with some problems to work on. And then we'll check into some more videos a little bit later. Okay. Looks like we have some sort of an equation here, and it says L is equal to 3.14 times R1 plus R2 plus 2D. And again, this is some sort of an equation that they give you in this sample book. This looks a little bit like pi to me, 3.14, but be that as it may. The example question says solve this for R1. So we want to get something that says R1 equals. Well, what I might do here, first of all, is let's get rid of this 2D on this side. So again, it's kind of reverse order of operations. I'm going to call it L minus 2D is equal to 3.14 R1 plus R2. So again, we're trying to get an equation that says R1 equals. So in that case, let's get rid of that because it's multiplying this quantity R1 plus R2. I'm going to divide both sides by 3.14, and I'm going to go ahead and finish it up here. So I'll get L minus 2D over 3.14 is equal to R1 plus R2. And I will now subtract R2 from both sides. L minus 2D over 3.14 minus R2 is equal to R1. So we can certainly write it that way. We could also get a common denominator too and tidy this up a little bit. I'm going to bring the R1 over to that side. That's equal to L minus 2D over 3.14 minus 3.14 R2 over 3.14. So when I collect all the terms, L minus 2D minus 3.14, everything is over 3.14. And so there's my equation in terms of R1. Let's take a look at a physics type equation where we talk about distance and velocity. And this is some sort of an equation here where I've got d and it's distance, and that's going to be related to these quantities. 3 times velocity 1 plus velocity 2 times 3 plus t, where t is probably time. And let's see, what else do we have here? Yeah, t is time in hours, and v1 and v2 are two different velocities. And this equation would talk about the distance covered over this particular physical system. And they want to know, in this case, they want to solve the formula for time. In other words, how much time is it going to take if I would know these other quantities, velocities and distance? Well, first thing I'm going to do is try to get all of everything else but my t onto the other side. So let's come back to that. I'm going to say d, first things first, minus 3v1, because I'm just going to get rid of that, subtract it from both sides, divided by v2 is equal to 3 plus t. All right, subtract 3 from both sides. T is equal to d minus 3v1 over v2 minus 3. And if I wanted to, I can go ahead and collect all my like terms. I'll multiply this by v2 over v2, and I'll have one denominator here, v2, and I'm going to get my numerator d minus 3v1 minus 3v2. So these are ways to manipulate equations to solve for any one of the quantities. And I'm going to go ahead and upload some stuff for you, and hopefully you'll be able to go ahead and do some problems and check back for some more videos as well.